So just a reminder that today we have quiz. But that's not a big deal. As I said previously, I will grade it very leniently. Also, don't forget to take the academic integrity quiz on Canvas. That will unlock course materials, so it shouldn't take too much time. And finally, we also have this simple assignment to set up your GitHub. Please do that. So that's the deadline is coming up. So I think last time I checked, I think 1/3 of the students have already submitted that assignment. Okay. So today we're going to talk a little bit more about C and specifically some C background knowledge. And maybe some of that will even help you in your by the way, did somebody forget this or just curious? Okay. Okay, let's get. So we let's say we have a structure and it's defined as follows, right? We have a field A, B, C, D, and E. So we have character A, integer B, character A, C, short D, and character E. So all these types are different sizes. So for example, characters are typically 1 byte in C. I mean, I'm not familiar with any architecture that for which it's different. Now, integer and short can be different according to different architectures, but typically integer is 4 bytes and short is 2 bytes. And certainly that's the case for x86 64. Those types, the way that we'll put them in the structure, so those fields, the way that we put them in the structure, they will be ordered according to the declaration. So that means we have to put A first, then B, then C, D, E. So irrespective of any other consideration that the compiler may have. So the compilers just have to follow the order that you specified. So it won't do anything else. So now, we also have to align each field in the structure such that we will be able to access the corresponding field efficiently, or in some cases, CPU architectures even require that. So, by the way, any idea why do we need to do that? So why do some architectures require that, or to do any alignment? Yeah, let's think a little bit about this, and let's come back to this question in a moment. So let's say we have a char A. So char A is going to be the very first element in memory. So initially, everything is aligned properly. That's the assumption of the compiler. So A goes first. So now we have to place B. But before we place B, we put a padding of 3 bytes. So any idea why do we need to do that? Why the compiler needs to put 3 bytes padding? Any guess? Okay, go ahead.
The size of the cache in the CPU.
Yeah, so the size of cache in CPU is like, at least for x86 64 is 64 bytes. So I guess the answer is a little bit tricky here, because typically the way that modern CPUs work, they will bring the entire cache line. But the traditional answer, just kind of something that will help you to intuitively think about this problem. Let's say we are not even dealing with 4 bytes, but let's say for x86 64, we are dealing with 8 bytes. So, and we just want to put an 8-byte word in memory. So 8-byte word typically can be retrieved or written by just one operation. So now if you don't align it, And just let's forget about cache for a moment. If you don't align it, then what happens is that whenever you want to write 8 bytes, and if it's like at the boundary of two different words, let's say 4 bytes from the first word and another 4 bytes from the second word. So then what happens whenever you write this 8 byte, you have to first read the first word, then you have to read the second word, and then you have to place a piece of it in the first word and write it, and then you have to put the second half of it to the second word and write it as well. And let's say, and this is going to be definitely more expensive than just writing 8 bytes, right? So that's something that helps you to intuitively think about this problem. Again, in modern architecture, it's a little bit tricky because we actually don't deal with words, we deal with cache lines. I mean, we're still dealing with words, but at a different level. So now, why do we need to have 3 bytes? So here we have a 4-byte element. So the idea is very much similar. Whenever we want to write 4 bytes, perhaps we still want to retrieve this word, a 8-byte word, whenever we replace the 4-byte piece. But we still at least want to have one write operation. So there is still a value of aligning at the 4-byte boundary. So therefore, the rule is that you're going to align type approximately like in most CPU architectures to its size, right? So if it's a 4-byte integer, then you're going to align at 4-byte boundary. If it's 2-byte integer, you're going to align at 2-byte boundary. So obviously, char doesn't require any alignment because it's just 1 byte. Well, that's almost true, but not entirely true, because, for example, if you want to write an 128-bit integer, which will be 16 byte in 64-bit architecture, which normally deals with 8-byte words, you only need 8-byte alignment, right? So you still typically don't go beyond whatever your architecture supports, right? So if 8-byte alignment is more than enough. So therefore, the alignment is actually determined by the ABI, application binary interface, which is specific to a particular CPU architecture and an operating system. So there, just we humans put some rules, and then the compiler follows these rules, right? And we humans put these rules because we have some knowledge about this architecture, and we know that what works best for this architecture, so to say, right? Okay, so now some architectures such as x86-64 don't actually require that you align these fields. It will still work if you just put 4 bytes right after 1 byte. It's going to be misaligned, but it will still work. So typically in x86, it will be slower, right? So there is still value in aligning those bits properly. So in some other architectures, such as RISC architectures, that's not even supported. So it can just fail. So either way, there is definitely value in doing this alignment properly. So let's continue, right? So let's say we have 3-byte padding because we have 4-byte element. So we add this 3-byte extra. So we are back to the 4-byte boundary alignment. Then we place C. So C doesn't require any alignment because it's just 1 byte. And then we want to put D. But before we put D, we have to align at a 2-byte boundary. So we have to insert extra 1 byte. Again, it doesn't matter whether it's like in this word or the other word, as long as it's 2-byte aligned. So then we place E. So that doesn't require any padding. And finally, do we need anything at the very end? Any ideas? Okay, go ahead. No, not null pointer, right? So, but do we need padding, right? Do we need padding? Do we need to insert anything? Okay, go ahead.
Do you want to add 3 more bytes so that it?
Yeah. So why is that? Yeah, that's correct.
So that it can at the end of a byte or like a 4 byte spot, like a 4 byte block.
Yeah, so but do you know what's the main reason for that? Yeah, so okay, go ahead.
It's like 2 words, that's why.
Yeah, so well, so okay, let's think about this for a moment. So technically speaking, I don't need this 3 bytes at the very end, right? So if I just consider that structure, I mean, nothing is going to be affected. A, B, C, D, E doesn't seem to be affected, right? Especially like, I mean, E is just 1 byte. So why do I even need to have that padding at the end? Well, that works for just one element. But let's say we have 2 elements. So let's say we have an array of the structures, right? So we have an array, not just one element. So then A, B, C, D, and E, whatever the alignment that compiler is going to place, will assume that the starting point is already properly aligned, right? So it has to be at least 4 byte aligned, and I will get to the in a moment why it should be at least 4 byte, but it should be properly aligned at the very beginning. So in other words, if you have a second element going after this, so again we have A, B, C, D, and E after this, the starting point has to be aligned properly. So and therefore we want to insert this 3 byte padding. So now you may have a second question. Why do we actually have that 4 byte alignment as opposed to, let's say, 8 byte alignment? Seems like we are running it on a 64-bit architecture. We are ready to deal with 64-bit words. Seems like natural to align at 8 byte boundary. Well, the reason is that, again, the compiler will take a look at the worst case scenario in the struct. And the worst case scenario for the struct is a 4 byte alignment. So it's the worst case scenario is int b. So that requires the strictest, that has the strictest requirement for alignment. Because whatever is 4 byte aligned is also 2 byte aligned and 1 byte aligned. But whatever is 2 byte aligned is not necessarily 4 byte aligned. And so on, right? So the worst case scenario is int b. So that requires 4 byte alignment. So therefore, I have to ensure that the structure at the very beginning is 4 byte aligned. So it just looks at the worst case scenario in all fields and just decides on this. So let's say if I have lon b rather than int b, then the compiler will have to make sure that it's 7 bytes at the very end, as opposed to 3 bytes. But here, the worst case scenario is just 4 bytes, so 3 bytes is sufficient. So that's the idea. So the rules may be a little bit complicated sometimes, but remember the compiler is not doing any magic here. It just follows strict rules. So this type requires that alignment, that type requires that alignment, so therefore I'm going to insert 3 bytes padding. Okay, and then I have 4 byte at most in my structure there. Therefore, I have to put 3 bytes padding at the very end. So the compiler actually doesn't do any magic, just follow the strict rules. And those rules are defined by the API. So each type has its own alignment requirements in the API. So the compiler has to keep track of the current alignment and its source corresponding pattern. So for example, at point A, it knows that it's 4 byte aligned. Then once it inserts field A, it knows that it's no longer 4 byte aligned. It's just 1 byte aligned. So therefore, it has to insert 3 bytes of padding. So the variant also needs to be padded. So so the rationale for this is mostly, let's say, consider an array, right? So an array of structure instances. Any questions so far? Okay, go ahead. Okay.
So we're it says D and C, and then there's that space in between.
Yes.
You couldn't just switch D in the space between, so it's then 1, 2, 1.
Yeah, so that's a good point. But you see, the first rule, ordered according to declaration, right? So the compiler will not do any magic, right? So the compiler will just follow the order that you specified. But you're making a good point. You as a programmer perhaps should think, you know, what's the best way to align, to kind of to place this fields inside the structure. So perhaps you can start with the largest first. So it's sort of greedy algorithm, right? So you can start with the largest largest field first, and then go with in descending order, right? So put chars at the very end. So if for you doesn't matter what the order is, that's probably the best strategy. So I would put int b in the front, then I would put short d, and then I would put all chars at the very end. And that definitely would be more space efficient. So that's a good point. Okay.
I was wondering, like, if you did the size of that struct, would it be 16 bytes then? If you ran that?
Yeah, just calculate what's the total size. 1 plus 3, 4, 8, 9, 10, 12. Did I miss something? Oh, wait a second. 4, 8, 9, 10, 12, 13. So it's 16, right? So that's correct, 16. Yeah, but let's compare it if we just have int b, then short d, and then so that would be and then all chars at the very end. That would be 4 plus 2, 6, plus 2, 8. Then you will have 9, and then you'll have to have 3 byte padding at the very end. So that's going to be 12, right? So that will be slightly more space efficient. So if you just rearrange some of these fields. Okay. So also recall that we can create our own types using type defs. So for example, we can have type def integer ID, and that means what I can do is basically use ID as a type instead of integer, right? So why is it beneficial? Well, perhaps at some point you may decide, you know, I don't want to use 4-byte integers for IDs. I want to switch to 8-byte integers. And by using this special type, you just need to change one line of the code as opposed to just changing it across all of your code, right? So it's really a good style to have type definitions like this. Also, you can define type def for structure. So let's say we have struct pt, like point. When we have two elements, int x and int y, and we can define a type point. So why is it useful? Well, sometimes you don't want to use struct pt, you want to just use point directly. So that's kind of shorter. I mean, it's really annoying to type struct in front of every type, right? So therefore it's again a useful thing to have. And sometimes you can even see that people would have struct pt and then have pt for the same type. So they wouldn't even name the type differently. So then you can use struct pt or just pt. Doesn't matter. Also, you can define type like we looked at last time for a function pointer. And let's say the function has two parameters x and y, and it returns an integer. So compare, let's call this type compare function. So that's how we can define a type for that function. So again, with this approach, you don't need to keep track of you know, whether, okay, I used this integer, but I really meant an ID, right? So it's already self-documented, so to say, right? So you don't need to even put any comments for that. So you can easily change types, integer to long, for example, right? And you avoid typed in struct. So struct pt versus point. Also remember that this function types, it's also very useful because imagine if you do something crazy like int, star, int, comma, that's like doesn't even look great, right? So when you type it in your code. So it's much better to use just compare function. So that's something that you can immediately see that it's a type that you want to do typecast. Any questions for type devs? Okay, good.
What's that symbol when it says like easily change types? Like,
Oh, that's just yeah, that's just basically an arrow, right? So just I think there's some problem in the slide.
okay, it's an arrow.
It just says integer we can change to long, right?
Okay.
Yeah, so that's yeah,
I
so
thought that was like the actual code.
yeah. I mean, it means that if you want to change integer to long, just use ID. Yeah, so that's not any of the C syntax. That's just some bug in the slide. Okay. So for header files, right? So recall that header files are used as an interface to your C code. So typically you would place function definitions in the head or any other so function declaration or any other declaration in a header file. So in a header file, for example, we can say that certain function, function name with two integer parameter exists, right? And you put int a, int b, whatever, right? But you won't actually place a implementation of that function. So you'll just declare that function there. So now the source file in C will contain the actual implementation. So in the header file can be included by other source files, and this is how you can define function across different C files. Also recall that, and you probably have seen it if you looked at the system headers, that in front of the header files, you have something like if and def file name h, define file name h, then you have header content, and then end if at the very end. So any clue why we need that? Any idea? Does someone can? Any guesses? Okay, go ahead.
Because you might reference the header file to multiple source files, and then it will get compiled over and over again.
Yeah. So, and not only this, not only from multiple source files, but let's say I'm including multiple header files in my source file. And that header file also includes the same header file, right? So there's, let's say I'm having types.h, and that's included by my source file, as well as, let's say, by some malloc.h, which includes types.h, right? So, so therefore, I'm going to include types.h twice. So, and I don't want to do that. So this is why it's I have that kind of protection at the very beginning of the header file. So what this definition will do, so the first time you include this header file, it will check if file name is not defined. Yeah, it's not defined yet. So then define file name.h. Sorry, file name h, right? Include the entire header content and exit, right? So now the second time you're going to include this header file, it's going to check, okay, is file name h defined? Yes, it is. So therefore, it will skip the entire header file. So this is why you won't compile it twice. And this is really helpful because you really don't know in a complex project how many times the same header file was included. Because again, it can be included indirectly through some other header files. It's really hard to keep track of it. And sometimes you have some compiler directives such as pragma once, which is kind of similar to this. there is some differences, but you know, fundamentally it's doing the same thing. Okay, so also recall how you can define constant in C. So let's say we have defined my constant 5, and then we what it effectively is going to do, it's going to replace every instance of my constant with 5. So why is it useful? Again, I don't want to put 5 in my code to hard code it. So it's better to put my constant and just, you know, if I want to change it later to 10, that will be replaced automatically, right? So I just need to change one line of code. So I don't necessarily need to specify numbers, and I can just have strings like hello. It will also replace my string with hello. Also, I can just, whether I need to put quotes or I don't need to put quotes, that depends on the context. Sometimes I want to put quotes also in front of it. Sometimes I don't want to do that. Just again, the compiler will not do anything special here. It will just effectively copy and paste. So it will just see my string, replace it with hello, and that's it. So we previously also talked about if and def, right? So there is also more general, you know, preprocessor command, which is called if. So if some condition, let's say, is true, then you will do certain things. Else, you will do some other things. So this is determined at the compile time. Just 1 second. So this is not something that will be determined at runtime. And the advantage is that maybe you have some code which is specific for x86-64, then you're going to compile it for this code. Or maybe there is some code specific to ARM64, then you're going to compile that code. Okay, go ahead.
Question I had with my string below is that if you put my string
Okay.
quotes in the implementation for it, would that have to be escaped? Or does this
Yeah, it has to be escaped, right?
So it would like string.
Well, wait a second. If you have to be, has to be escaped. Yeah, I think has to be. That's a good question. Do you have to? You want myself a good right now. It's a good question. I thought that it should be escape. I mean, it won't. I think it should escape it here. Yeah. Yeah. So yeah, whether it's absolutely required or not, I don't recall right now. We can check that.
Yeah, I'm just thinking if you said like define and then like give some word and you have to say that like string.
Yeah, but your question is when I put quotes before hello, do I need to put an escape sign before quote, right? Is that your question?
If you implement, if you in the code and use the define for my string, but that was inside of quotes,
Yes.
would it go? Would it interpret that as a string, or would it interpret that as like the macro?
Well, if you put in quotes then your question is different. If you put my string in quotes, yeah, then definitely the compiler will not treat it as a macro anymore. It will treat it as a string. So the compiler will only replace it if you don't put it in quotes. So this is why if you want to put some quotes, you have to put it inside this definition, right? So not outside. Does make sense? But sometimes you don't want to put it in quotes. In fact, C process is actually trickier. So sometimes it would you would also want to you know, you would also want to kind of make it convert hello to the quoted string, so to say, right? So there is a way to do that as well, right? Yeah, it's a little tricky. So, and I would actually recommend for strings to be a little bit more careful, right? So if you want to put quotes there, right? If you don't want to put quotes, I mean, typically you would want to put quotes right away, unless you are writing some maybe inline assembly code inside C, then maybe, you know, some circumstances you don't want to put quotes. So let's say you want to call some function, and that doesn't have to be quoted. Okay, so the idea of if my condition is that you check it at the compile time, not at runtime. So you won't even compile that code if it doesn't satisfy that condition. So in the same thing is with if def. So the one that we have looked already. I mean, we looked at one way to use it, but certainly not the only way to use it. We can. What we can do is basically we can also use if space defined, and then certain condition. That's also possible, or we can just use if def. Or we can have if not defined, or the same as if and def. So there are different versions of that. So the difference here, let's go back to the previous slide. So the difference here is that if I specify if and def file name h, I'm not actually checking the value of file name h. I'm just checking whether this definition even exists. Whether file name h is 1, 0, or any other value, I don't care. I just want to see if somebody has defined that. So and then we define file name h. So sometimes you will see people will say file name h space 1, define file name h1. That will be also fine, right? So, but you will also specify a value for file name h. So in that case, def just determines whether a certain value is defined, whether a certain constant is defined. Whereas if can also check the specific condition. So you can say if file name h equals to 1, then do something, right? If it equals, else if equals to 2, do something else, and so on, right? So if is more general. So again, using constant as magic numbers in code, this is really bad. It's a bad style. So it's much better to define constant like 5 and just use constant everywhere. So then you only need to change one line of code. So sometimes it's even better to specify something like static const int, and then a name of the constant equals to 5, because it also includes type information. So by looking at this, the compiler knows that it's in int type. Maybe you want to define one type, that's also fine. Maybe with int and lon it doesn't matter too much, but sometimes it matters, or there is some subtle bugs that can happen without, if you don't specify the proper type. So therefore it's a little bit safer. And especially if you use floating point numbers, that you can specify 5, but 5 as a floating point is different as 5 as an integer. Or sometimes when you multiply numbers, you don't want to rely on some magic how the compiler will, whether compiler will expand it to 64-bit or will not expand it to 64-bit. Those rules can be complicated. So it's sometimes better to explicitly say what type it is. So also you can use const with pointers. So for example, pointer const data. So const int star p means that we have a pointer we have a pointer which we can change if you want, but it points to constant data which we cannot change. So some read-only data. So typically, let's say you have some string const char, and then you have some string. You cannot modify the content of the string, but you can modify the pointer. So the opposite is also possible. So you can have const pointer to variable data. So you can modify data, but you cannot modify the pointer. So the pointer can be assigned just once. So that's int star const p. So don't confuse those two things. And also sometimes it's possible to have both const pointer to const data. So that's going to be const int star const p. So just make sure you understand the difference, right? So variable data versus the pointer that and the pointer that you can change.